Welcome back to Integral Calculus. In this video I want to talk about another physics application of integration, and that is hydrostatic force and pressure. So hydrostatic force and hydrostatic pressure are forces and things that are caused by a fluid, typically water, which is where the hydro comes in, but it comes from some kind of fluid pushing on something and exerting a force on it. Okay, usually you have like something submerged in water, or you have like the side of a dam blocking a river or something like that, and the water wanting to push against the sides of the dam or push something down is what we're talking about here. Okay, so let's get right down to it. If you've never heard of pressure, that is fine. Let's talk about it briefly here. So like always, we will start by understanding what happens when everything is constant, and then go on to when things are allowed to vary, and that's where the calculus comes in. So first of all, what is pressure? So if we have a force, let's say we have a constant force, F, acting on an object, and it has a surface area, A. Okay, so pressure is force per unit area. So the pressure in this situation where everything is constant, the area is not changing, the force isn't changing in different parts of the object or anything, the pressure we usually call P, and it's just the force times the area. Okay, so pressure is in general force times, force per area, sorry, force divided by area. Okay, so what are the units? Well, in SI units, force is measured in newtons. So this is going to be newtons divided by an area would be measured in meters squared. And units of newtons per meter squared are called pascals. We abbreviate it PA, and that's called a pascal after a mathematician / physicist named Pascal, believe it or not. Okay, so fine, right? You've probably heard of like tire pressure, and that's the pressure of the air pushing out on the sides of the tire and things like that. When an object is submerged, there's force pushing down on it because gravity is pulling the water down onto the submerged object. And this is what we call hydrostatic force. And then the pressure is, of course, just the hydrostatic force divided by the area. The interesting thing about pressure is that you can figure it out based only on the depth. Okay, so say we have like a square plate, and it has area A down here. Then the hydrostatic force is just going to be the force of the water pushing down on top of it. So I think of it like having a big box of water on top of this this thing here, something like that. Okay, so we have this tall column of water, and let's say this is height h. So the water is being pulled down. There's this force of gravity pulling the water down onto the area, and of course that's going to depend on h because h tells you how much water is on top of there. The taller h is, the more water. Okay, so the pressure, and again, this is where h is constant, everything is constant here. The pressure is going to be the weight of the water divided by the area of the plate, which is A. Okay, but we know how to find the weight of the water, right? That's mass times gravity. So this is the mass times gravity. Let's say that's 9.8 meters per second squared. And well, what is the mass? Oh, what's the mass of water? Well, sometimes we talk about the mass density, which is 1,000 kilograms per meter cubed. That's the mass density of water, or the density of water, times the volume. This is actually going somewhere, believe it or not, times 9.8 meters per second squared. Okay, oh, and all this is divided by area. Okay, fine. But the thing to realize is that the volume is the area times the height. So what we can do is we can say, okay, well, the 9.8 and the 1,000 combine. So we get 9,800. And then the kilograms combined with the meters per second squared, that makes a newton. So this is really newtons per meter cubed. That's these three units all together. And then the volume is actually just the area times the height. and we're dividing by the area still. Okay, so the areas cancel out. That's how pressure works. It doesn't actually depend on the area because it's like pressure, the force per area, per unit area. Okay, so in the end, we just get pressure is 9,800 newtons per meter cubed. That's the weight per unit volume of water times the height, or the depth of the water. So H is the depth of the water here, or the depth of the plate, really. Okay, so that is a really good thing to know. If you want to do this in standard units, you can. It turns out to be 62.4, because, you know, of course it is, times H. So instead of 9,800, we have 62.4, and then these would be in pounds per square foot. I don't really like imperial units, but, you know, some people do, so there it is. Okay, so everything's easy. You just multiply when you're doing standard stuff where there's no changes in anything. The plate is at constant depth, nothing weird at all. Of course, the calculus comes in when you start having things be non-constant, in particular non-constant depth. So let's look at an example. We have a fish tank. It has a square base and rectangular side, so it looks like a big box. We have a square base, and the base is 3 meters long, and it's a square, so each side is 3. And it's 2 meters tall, so it's going to look something like this. That height is 2. And first, let's find the hydrostatic force on the bottom of the tank. And then we'll find the hydrostatic force on one of the sides, which is actually a calculus problem. So on the bottom, it's easy. The force is just the weight of gravity. So, sorry, not the weight of gravity, the weight of the water, which is the force caused by gravity pulling on the water. So what's that going to be? Well, I guess we're going to have the area, or how much water do we have is the volume. That's the volume of water times the density. Let's call this the weight density, which is, what's the volume? 3 times 3 times 2 is 18, and these are meters cubed. And then times weight density of water is 9,800 newtons per meter cubed. And we end up with some number, I think I get 176,400 newtons. Okay, so fine. No trouble there, right? We didn't even have to do anything with pressure. What about the side? So now I'll draw the bottom again, even though I don't really need it. But let's say we just have this one side of the fish tank sticking up. Okay, so that height is 2, this length is 3, and this is still 3, even though we don't need it. The thing to realize is that the force is pressure times area. Okay, because pressure is force over area, you move the area to the other side. And now, how am I going to figure out the pressure? If I can figure out the pressure, then I can figure out the force, right? Okay, the thing to realize is that pressure is proportional to the depth of the water, and that changes at different places on this vertical plate. Okay, so if I just draw my vertical thing here, let me not draw it like that. Let me draw it head on. So let's say I have this strip here, that would be like this strip here. Different sections of this piece of glass are going to be different depths, so they're going to experience different hydrostatic pressure. Okay, so let's say this distance is y, like it's on the y-axis. And how tall is the whole thing? Well, it's 2. So let's say this is 2, and this is depth 0, depth 2. And let's make a little strip, delta y, and like always, we'll assume that everything is constant on this little strip. Okay? So I want to first find the force on the strip. Or let's call it a slice to maintain what we've been doing. So the force on one slice is going to be the pressure on the slice, which again only depends on the depth, times the area of the slice. Okay? Because I can assume that that slice is thin enough that the pressure is constant everywhere on the slice. Okay, so what is the pressure on the slice? Well, the pressure is going to be the weight of water. That is newtons per meter cubed, 9,800. And then, well, it depends on the depth, right? So my equation up here says that when everything's constant, the pressure is 9,800 times the depth. So in this case, the depth is y, and that means that the pressure is 9,800 times y. Now, what is the area of one of these slices? Well, that's a rectangle, so that's not so bad, right? This bottom is 3, so the area is just going to be 3 delta y. Now, of course, if I want the total force, I just need to add up all the forces on all the pieces. So the total force, or sometimes this is called the net force. The total force is going to be the integral, that means add everything up, of the force on each piece. So 9,800 newtons per meter cubed times 3y delta y. Okay, where am I integrating to and from? Well, where can I have a slice? Anywhere between y equals 0 and y equals 2. I integrate from 0 to 2. Always, where can I have a slice? Okay, so you do this integral. It's pretty easy because you're just integrating y dy. Oh, that should be a d. You know, you take a limit. Delta y turns into dy. So you do this integral. You're just integrating y dy, and you get 58,800 newtons. Okay, so yeah, not too bad. The plate was a square, so of course this is going to be somewhat simple. What about a little more complicated example? Suppose we have water sitting in a reservoir and it's shaped like a parabolic cylinder. Ooh. So the side is going to look like this. Then it goes out like this. Something like that. So these are straight lines. So it's kind of like a sheet of paper folded up into a parabola. And let's say one face is shaped like y equals x squared. So that's telling us how wide the parabola is. And the water is 10 meters deep. So I just have this one face over here. And I want to figure out the hydrostatic pressure, or the hydrostatic force on that side. Okay? So one thing to realize is that the length here, this distance, doesn't matter. The pressure, and therefore the force, is only dependent on the depth of water, not how long it is in the opposite direction, or in the perpendicular direction. Okay, so let me just draw the picture how I want it. I only care about this face, and since it's y equals x squared, I'm going to put the origin right there. And the water is 10 meters deep, so I'm probably going to end up going to y equals 10, something like that. Okay, so the process is the same. One of the really nice things about pressure is, since we all are always talking about depth, we're always drawing horizontal slices. There's never a question of, oh, do I draw a vertical slice or horizontal slice? Pressure is proportional to depth, which is always a vertical sort of thing. So I want to draw a horizontal slice, and let's see. Oh, you know, what am I going to do here? Oh, I know. I need to find that because that's the depth of the water for the slice. And then I'll figure out the area of the slice. Let's call this delta y. So let's see. I have force equals force on one slice equals the pressure times the area. Okay, so what is the pressure on one slice? Well, that's going to be that depth there. That is 10 minus y. So that's the height, and then times 9,800 newtons per meter cubed. I guess 10 minus y should be measured in meters, of course. And what's the area? That's a little trickier. I want to find this distance between here and here. Those are the x values. So over here, x is equal to the negative square root of y, taking y equals x squared, which means x equals plus or minus square root of y. And over here, x equals positive square root of y. Notice that the x values do depend on how deep it is. So the area is going to be that length, which is 2 root y, times the height, which is delta y. Okay? So that 2 root y is the hard part here, and it's actually just a difference between these two functions. It's root y minus negative root y. Okay, so the total force is going to be the integral. I can have a slice anywhere between y equals 0 and 10. Then I'm going to integrate this function here, because I'm adding up all the forces. So I have 9,800, then I have 2, and then I have 10 minus y, I have a square root of y, and I have a dy. Okay, so I will leave it to you to get a number for that. I certainly don't care what the number is. you can do this integral pretty easily, right? You can just pull out the 9800 times 2, so that's going to be 19,600. And we have integral 0 to 10, and I would do 10 root y minus y to the 3 halves. Okay, so you get some integral like that, you get a number. Let's just make sure the units check out. The units on this were the newtons per meter cubed. Units on 10 minus y were meters. Units on square root y were meters because that was the distance in the x direction. 10 minus y is the distance in the y direction. And dy is measured in meters. So yeah, we've got newtons per meter cubed times meter cubed. So these are all going to have units of meters cubed. And we're going to get something in newtons, which is pretty good if you're looking for a force. Okay, so you can finish that on your own. But the general idea is what I really want to impress upon you. You slice everything up, look at a general slice, figure out what happens on that slice by assuming everything's constant, and then just integrate to add up the contributions from each slice. Okay? So with that, I think we'll be done. I'll see you in class.